Hello there, Mr. Sutton here, bringing you the Pre-Cal Honors 2-1 lesson on solving polynomials by factoring. In this one, we will be solving polynomial equations by using a number of factoring techniques, including taking out common factors, quadratic form, and factoring by grouping. As a real-life application, we'll figure out when the rate of inflation for a country will be 0. Let's begin by defining what a polynomial is. You've probably heard the term before. What we're talking about a series of power terms that have only whole number powers. So for example, something like x cubed minus 2x squared plus 9. These are all x to some power, and the power is either 0, 1, 2, 3, 4, numbers like that, counting numbers. No fractional exponents, no negative exponents. And this 9, if you're wondering where the x is, well, we have an invisible x to the 0 there. So we can talk about the degree of polynomials. The degree of a polynomial is just the highest power. So for example, this one here is a third degree polynomial. So we're going to make a little bit of a chart because some of these degrees have special names, and I want to give you a few examples too. So I've got examples of various degree polynomials, and you can have more than a fifth degree, but I only felt like going up to 5. And I'll give you an example and the special name. So an example of a 0 degree polynomial would be 7x to the 0. And since x to the 0 is really 1, this is really just the number 7. So yeah, 7 is a polynomial. You've been using polynomials this whole time, really since kindergarten without even knowing it. Now the special name for this kind of polynomial is a constant, because it doesn't actually change. There's nowhere to really plug in a variable or something for x to make it change. Now a first degree polynomial is something like 3x to the first, which of course we would just write as 3x. And these kinds of functions, we've used these for a while too. These are linear functions, but they also count as polynomials. Second degree, that would be something like x squared plus 4x minus 1. And we've done a whole bunch of work with these very recently. These are quadratics, and they are polynomials as well. Third degree, that would be something like 8x cubed minus x squared plus 2. These are called cubic polynomials because x to the third is also x cubed. And then fourth degree, that would be like 2x to the fourth plus 8x. This is a quartic polynomial. And finally, fifth degree, something like negative 10x to the fifth plus x cubed. We call this a quintic polynomial. Now, it's worth noting that you can also talk about the terms within polynomials using these special names. For example, this 8x in this quartic polynomial, we could say that this 8x is the linear term of this polynomial. So it gives us some flexibility to have these names. Now, there's somewhere else that this degree idea comes into play, and that's with something called the fundamental theorem of algebra. This basically says that a polynomial has as many solutions or roots or zeros or x-intercepts as its degree. Now, there's a few caveats to this, but first let's just give an example. So for example, if you have a cubic polynomial, that would have exactly 3 solutions, guaranteed. Now here's the fine print. Some of those solutions could be duplicates. You could have a double root. You could also have imaginary roots. So if you count duplicates and imaginaries, the number of solutions and the degree will always match up with polynomials. Kind of neat. At this point, we're going to go through a few different types of polynomials and how to solve them. So this is a special case where we have terms that all have variables. If all your terms have variables, there's a few do's and don'ts in this situation. Let's go over the don'ts first. There's a big one: don't divide by the variable. It's tempting, right? Just to divide by an x and have 8x squared minus 72. But if you divide by x, you don't really know what you're dividing by. For all you know, you could be dividing by 0, which would be a huge no-no. So unless you can prove beyond any shadow of a doubt that x can't possibly be 0, you're not allowed to divide by a variable. Okay, so let's go over what we can do. Do try to factor out that variable. And in general, you should always begin these problems by trying to take out the greatest common factor. So we can definitely take an x out of both of these. We can do a little bit better than that, though. We can take an 8 out as well. 8 and 72, both divisible by 8. So if we take out an 8x, that leaves us with x squared minus 72x divided by 8x is just 9, negative 9. And in general, you're trying to get these things down to quadratics, because if you can get a quadratic like x squared minus 9, we know that quadratics can be solved by factoring, square rooting, or even the quadratic formula if you need to. We have a lot of power when it comes to quadratics. So there's a lot of different ways you could do this one. Pause the video and pick a way of dealing with x squared minus 9 and then bring it back in. All right, so I chose to just factor a little bit more. I'm going to bring down this 8x. X squared minus 9, that's a situation with a squared minus b squared. So I know I can just square root those and do the plus and minus parentheses. So we've got x plus the square root of 9, x plus 3, times x minus 3. And now setting each of these factors equal to 0 and solving, we've got x equals 0. That'll zero out that 8x factor. X equals negative 3 for that middle factor. And x must equal 3 for that last factor. Another way you could have done this is you could have actually just done x squared minus 9 equals 0, added 9 and square rooted both sides. That would have also given you that plus or minus 3. This next example is another special case that we can solve by factoring. With this one, this is actually something called quadratic form. Quadratic form is something that's not really quadratic. I mean, this is x to the 4th, not x squared. This is a quartic, but it has the form of the quadratic trinomials that you're used to dealing with. Quadratic form is something in the form x to the 4th plus something x squared plus c. Or it really could be anything where the first exponent is twice the second exponent, and you have a constant like x to the 6th, x to the 3rd, and some constant. So any of those count as quadratic form. Now the nice thing about these is that you can actually treat them like a quadratic in terms of solving it. The only catch is that you're going to use x squared or whatever that middle exponent is instead of x. So you can try factoring it with x squared, or don't try it at home, but you could even use quadratic formula, letting x squared equal the quadratic formula. So any of those. So pause the video and pretend for a moment that this is a quadratic and strategize what you would do to solve for x. All right, so this is one that you could definitely factor. If this were x squared minus 16x minus 80, we'd be asking for numbers that multiply to 80 and add up to negative 16. So let's see here. We've got 1 and 80. That doesn't work. 2 and 40 doesn't work. How about 4 and 20? Well, if I had positive 4 and negative 20, that would add up to negative 16. So I'm going to split this up then into x squared minus 20 and x squared plus 4. So basically like if I was factoring a quadratic, only I have x squared here instead of just plain old x. At this point now, since I've got two quadratics, I can just solve each of these individually. So if I have x squared minus 20 equaling 0, and I have x squared plus 4 equaling 0, solving this first one here, I would add 20 to the other side, and I can just square root this at this point. So this would be x equals, don't forget the plus or minus, and I have to split up the radical. This would be radical 4 times radical 5. So then plus or minus 2 radical 5. So go ahead, pause the video, and do this other branch here. All right, so for this one, we'll subtract the 4. Square rooting both sides. Since we have a negative inside a radical, we can take that out as an I, and then the square root of 4 is 2. So this is plus or minus 2i. And one more thing worth noting here, notice how many solutions we have. We have 2 here and also 2 here. So counting these imaginary solutions, that's 4 solutions, which we would expect with the fundamental theorem of algebra, because the degree of this was the 4th power, 4th degree. We're going to do one more example, and this is all going to be the backstory for example 3 on your handout that you see. So let's say we have some economic turmoil, and a country's rate of inflation can be modeled by this polynomial, where x is number of months since the start of the new year. We want to know when the prices are neither decreasing nor increasing. In other words, this function, the inflation function, equals 0. So setting this whole thing equal to 0, we're essentially trying to solve one of these crazy polynomials. So real life application here. So I said this was a special situation because look at how many terms there are. We've got 4 terms. Do you happen to remember what we can do or try to do when we have 4 terms? Oh yeah, factoring by grouping. So for 4 terms, you should always try factoring by grouping. Of course, you should always try taking out a common factor before you do any of this other stuff. But if you look here, there's no common factors to take out. So we are going to do this by grouping. Before we do that, take a quick moment and see how many solutions you expect to get out of this one. Did you say 3? That's right. Third degree, using that fundamental theorem, we're expecting 3 solutions. So we've done grouping before. Pause the video and see if you can apply it here to solve for x. All right, so we have to take a common factor out of these first 2 terms. All we can take out is x squared. That leaves us with x minus 5. And for these next 2 terms, the biggest common factor you can take out is actually negative 32. So that leaves you with x, and 160 divided by negative 32 is negative 5. Since we have x minus 5s, we can take that out as a common factor, leaving us with x squared minus 32 in the other parentheses. And now we're down to the point where we have a linear and a quadratic, so we can definitely just go ahead and solve those. So x is just going to equal 5 for this first factor. For this other one here, we have x squared minus 32 equals 0. So that means that x squared equals positive 32 if we add 32 to the other side. And if I take the square root, I've got a plus or minus, and I can split 32 up into 16 and 2. So this ends up being then plus or minus 4 radical 2. And these apparently correspond to the months at which inflation is 0. This concludes our look at factoring polynomials to solve them. Until next time, Mr. Sutton signing off.